Good day and welcome to another class on basic PLC. Today we are going to be looking at PLC Architecture. PLC Architecture. What is PLC Architecture? By architecture, what do we mean? We mean the arrangements or layouts of the components of a system so as to what? Identify that system. That's what architecture in this context means. How is the PLC laid? What is the components of that system so that we can uniquely use that to identify the system? Let us go inside of a PLC itself. The picture on your screen shows us the internal structure of the PLC. The PLC contains the central processing unit, the CPU. It contains the memory. It also contains the peripherals like the inputs and the output circuits to the PLC. We also have a communication port for communicating with the outside world. And then we have the AC power supply or the DC power supply to the PLC. The PLC is made up of an optical isolator called an isolation barrier. This isolator helps the PLC to ward off things like high voltage, short circuits, among transient currents that could damage the central processing unit. Isolation barriers will be looked into while we study basic electronics, how they operate. The PLC also contains the CPU contains an executive program. What is an executive program? The executive program tells the PLC how to execute control instructions as contained in the user program. This program is stored in the non-volatile memory, meaning that the program will not be lost if the power is removed. It also helps to tell the PLC how to communicate with other I/O devices that are connected to the PLC, such as the programming device and the other networks through the Ethernet port, and also how to perform what we call housekeeping, that is, perform internal diagnostics of the PLC. Now, there are 4 basic operations on how the PLC works. Number 1, the PLC is a workaholic. I used to say that. It performs first what we call the input scan. The input scan detects the state of all the input devices that are connected to the PLC. So which means it keeps on checking if there is any input that has changed state. So it runs this scan in milli and microseconds. It scans all the inputs connected to it so as to update it. The number 2 basic operation of the PLC is it performs the program scan. The program scan, when after updating this information, it updates the program based on what the user has actually imputed in its memory. So, is there any change? For example, you have a normally closed or normally open contact. And then the program says whenever the normally open contact changes states, you should perform a certain operation. Probably to shut down a valve, to on a pump, or to turn off a steam supply. Now, when this happens, it updates that program and then move on to what? The third one, which is the output scan. Now, the output scan now means it can now execute whatever information it has now received by energizing all the outputs that are involved or connected to the PLC. So, like I said, immediately it scans the inputs, it updates the program, and then updates the outputs by way of then on-ing the valve or switching off the supply, the output supply to whatever thing you must have connected the PLC to. The fourth is the housekeeping. Housekeeping involves the internal diagnostics of the PLC and also includes communication with other peripherals that are connected with the PLC. So each time the PLC is on, the PLC runs a scan, we call it PLC Scan. So it runs by doing the following. It checks the status of the contacts connected to it, of all contacts, and then it executes the program, and then updates the output. So when this is completed, it goes back, it checks. So this is called the scan. This is the PLC scan. Okay? So this is called the PLC scan. So this PLC continually scans by checking the status of the contacts connected to it as inputs, updates the program, and then executes the program, and then updates the output, and then it goes back and repeats. So it flows in this pattern. So this is the PLC scan. So should there be any faults along the way, the fault indicator will be updated as it goes by. Now, I also like you to look at the internal structure of the PLC as shown on your screen. This is the PLC 5 system. The PLC 5 system is similar to that of the PLC SLC 5, the Allen Bradley PLC, which I just showed you. Okay? So before you can see the power supply, you can have the CPU. You can see the CPU by the left. You can also see the back plane of that PLC, the I/O modules, the chassis, and other spare slots for expansion. So this is a modular PLC, which means it can be expandable. So these are the internal structures, should in case you are not able to see what was in the SLC PLC. So that is the structure of the PLC. Now, PLC contains three basic sections like we have mentioned. Number one is the CPU. We have the CPU, that is the central processing unit. We have the memory, just like in the computer. You have the memory, and the memory we know we have the electrically programmable read-only memory. We have the RAM and so many other kinds of content that the memory has. We also have the input and output section, which are used for communicating with the outside world. That is the peripherals. Okay? So the I/O device contains what we call the DAC, okay, and the ADC. So at the input, we have analog to digital converter. That's the meaning of ADC. And then at the output section, we have digital to analog converter, because the PLC is a digital device. It's a digital system, just like a computer. So all information that is gotten from the outside world will be fed as an analog input to the PLC. For example, in ones and zeros. Probably you type in a computer, you type A. You know that A does not actually mean A to the computer. In the ASCII code, it could mean 0110, So it could mean something else, okay? But in strings of zeros and ones. So that is how the computer processes information in binary forms. So when this signal is picked up, it is converted from the analog to the digital converter. And when the PLC performs all that it needs, it goes back to convert it to the analog as the output. For example, you could connect to the output a HMI. HMI is the human-machine interface. So this HMI is like an analog system because we, in the real world, we view things in an analog form. So there is a conversion between the DAC, ADC, and the DAC inside of the PLC. The PLC also contains things like input relays. This is the superior function that the PLC has over the traditional relays. So you can call up virtual relays in the PLC. You can call up virtual counters. You can call up virtual timers in the PLC. These are contained in the PLC. So instead of getting real-life relays, most times you can also call up the countless virtual inputs and output relays that you can find inside the PLC, okay? Now, PLC also contains what we have, or rather the PLC structure can be an open or closed architecture. What do I mean by open or closed architecture? An open architecture allows the system to be connected to various devices made by different manufacturers. That's what an open architecture is all about. So, for example, let me give you an example of, let's say, your phone. Okay, you have your phone, and then probably different makes, a Techno phone, an Itel phone, different types of phone, but uses a common charger. It's an open architecture, which means you can use a Techno phone to charge an Itel phone or to charge any other kind of phone. But an iPhone is an example of a closed architecture. So a closed architecture is a system which the designer makes it difficult to connect devices and programs by other manufacturers. So in other words, you must have to get an iPhone's charger to charge an iPhone. So you cannot use an Android phone to charge an iPhone. So that is just a quick example of an open or closed architecture. So by this, I mean that for an open architecture, you can use different kinds of sensors as an input device made by other manufacturers, as well as output devices used by other manufacturers that can interface properly with the PLC. Whereas a closed architecture, you must have to get the same product as produced by the same manufacturer. For example, if it's an Omron PLC, probably you need to get, for example, you need to get an Omron sensor and Omron output to run for a Omron PLC. That is an example of a closed architecture. So by looking at architecture block diagram, the PLC architecture can be summarized in this block diagram. All right, first we could have the input module. So the PLC all PLC must have an input module. From the input module, it must be connected to what? To the central processing unit, which we have been mentioning since, processing unit. That is the CPU. And the CPU, after processing, must have an output module. All PLCs have this. This is the architecture of the PLC, okay? And then the PLC must also have the ability to be written to and to communicate with other PLC devices. For example, you could have the programmer. So from the programming device, you can write to the PLC, or you can do what? You can upload from the PLC. You can also have an operator interface. an operator interface could be a HMI. HMI means human machine interface. Okay? And you can also have communication, okay, where it can also communicate with other devices by way of using probably a networking with other devices. So this is basically the major components of a PLC. And then the PLC definitely has to also be powered by a power supply. So the power supply can be from an external source, or it could be a compact PLC where everything can be, embedded as a single unit of the PLC. Now let us look at the kinds of memory that may be obtained in a PLC. So a memory unit is connected to the CPU, which contains program of logic, sequence, and I/O operation. Now, depending on the kind of PLC, there are 4 types of program memory one can come across in the PLC. Okay? So we have the RAM, that is the random access memory. These are the 4 types of memory you can come across in the PLC. 4 types of memory contained in the PLC. Number 1, you can have the RAM, the random access memory. You can have the EEPROM, electrically programmable read-only memory. We have the EEPROM, electrically erasable programmable read-only memory. And then we have the FL-ROM, that's the flash ROM. These are modules that are available, and each of them has the advantage and disadvantage in their usage. You may not find all these memories in one PLC. So you could find having a RAM and an EEPROM, or a RAM and any other of these read-only memory in the PLC. Now, there are the ROM, like we know, is volatile memory. It's a volatile memory. Anything stored in the RAM, rather, is volatile. Why the ROM is non-volatile? It has been basically pre-programmed into the chip, just like the OS in a computer. So whenever you boot up a computer, you have some information already as being stored by the programmer. So it contains some information that are stored in the ROM. So once programmed, the program is stored in the ROM chip. Whereas the PLC manufacturer utilizes the ROM, that's the read-only memory, to store information about the PLC. And some of this information is what we call the executive information. And what is this executive information? This executive information, which is stored there, composes of permanently stored program that directs all system activities that are contained in the PLC. So that executive program will tell the user program on how to run and the communication with other peripherals that are connected in it. The system memory also contains routines that implements the PLC instructions, the instruction set, which is composed of specific control functions such as logic, sequencing, timing, counting, and arithmetic functions. We also have the application memory. So in other words, we have the system memory and the application. So the system is basically for the manufacturers, the information, and then we have the application memory. Under the application memory, we have the data table and the user program. So this is where we write our program. This is where we manipulate. Okay? The system contains the executive program. So the application program, like I said, contains the data table and the user program. The application memory is divided into two, like I just said, and the data table basically stores any data associated with the user control program, such as the system input and output status, and any stored constants or variable or preset values, which can be manipulated, stored, changed for any control purpose. The user program area is where the program instruction entered by the user are stored as an application control program. So this is the area that we use. This is where we write our program. This is the area that is made available for the operator or the programmer to access. Okay? So this is what we call the memory map. This is how the map of the PLC, the memory map is composed. So we have the system application and the system memory and then the application memory. So having said that, this is all about PLC architecture. We looked at the kind of memory that the PLC possesses. We looked at the basic block diagram of the PLC architecture. We mentioned there is an input. We have mentioned there is a CPU. We mentioned there is an output module, as well as a way to communicate with the outside world using ports, that is, using the programmer and then the operator interface. So this is the basic structure of a PLC. A PLC must have a power supply. It must have a CPU. It must have an input device or input module. It must have an output module output module. And then it must also have a communication port where it can communicate with the outside world. This is basically the kinds or the structure of a PLC. At this junction, we are going to be stopping here so that in the next class, we will start the different OEM PLC softwares. Thank you. See you in the next class.